Hello students, in this video we'll solve a Lower Michigan math competition problem related to angle bisectors in a convex quadrilateral. Let's suppose that A, B, C, D is a convex quadrilateral. And let's suppose further, let's prove that if the angle bisectors from A, B, and C meet at a point P, that means they're concurrent at that point P, then the angle bisector through D also intersects P. Then the angle bisector through D meets P. And what else? And we get that A plus B, AB plus CD is equal to AC plus BD. So let's prove these relationships over here. Okay, great. So let's draw a configuration. So here's our convex quadrilateral. Of course, you're thinking like a square. It's trivial for a square, right? There's our convex quadrilateral, A, B, C, and D, right? And so let's think of what's going to happen over here. So if I draw the angle bisector over here, I draw the angle bisector over here, I draw the angle bisector over here, and we're lucky and they meet over here at this point P, okay? And so of course this angle over here and that angle are the same, this angle and that angle are the same, and then this angle and that angle are the same. Great. So that's the configuration we have, and they meet at this point P. Now let's think about the properties of angle bisectors. What do we know about angle bisectors? I know that the points on AP, so points on AP are equidistant from AB to BD, from AB to AD. Okay, what does that mean? It means the distance over here, that's perpendicular, that distance, if I draw a perpendicular over here, why do those have to be the same? That's perpendicular over here, not perpendicular. That's perpendicular. Those distances have to be the same because those triangles are similar, right? In fact, they're what? They're congruent because they're right. So in other words, those distances are equal to each other, right? Great. Now apply the same reasoning, right? So points on what? Points on BP are equidistant from what? From AB to BC, AB to BC. And finally, points on CP are equidistant from what? CP is going to be a CD, from CD and BC, right? Okay. Great. Now what does that tell me in particular? In particular, since P is actually on those line segments, so P is equidistant from what to what? From AD, to what? Well, AD to AB, AB to BC, BC to CD. Huh, that's cool. So that point over there is equidistant, which means what? It has to go through P, which means it's the angle bisector, right? So hence, P is on the angle bisector at D. And it tells us more actually, right? So that point P is concurrent with all of those angle bisectors. That's beautiful because now what that gives me is that tells me, hence there has to be a what? Hence P is also the center of a circle inscribed in the quadrilateral. Great. Okay, so there's a circle inside here. It's not going to be the scale. There's my circle. Like that. Excellent. Let's call this point over here E. Let's call this point over here F, G, and H. Okay? Now, what do I know? I know that DG is equal to DH by tangency. I know that AH is equal to what? I know that AH is equal to AE, etc., right? I get all those tangency requirements. So now let's go back to our problem statement. I have to prove that A plus AB plus CD. Let's look at AB plus CD is going to be AE plus EB plus CD is going to be what? CD is going to be CG plus DG, right? I just do those decompositions. Now by tangency, what do we have? By tangency, AE is AH. That's AH. By tangency, EB is BF. By tangency, CG is CF. And by tangency, DG is DH. By tangency. Excellent. Now what is this over here? BFCF is what? BFCF is BC. So that's BC plus what? AH plus DH is AD. And what have we proven? We've proven that AB plus CD is what? Is BC plus AD, which is this statement over here. So we got it, right? So what does this tell us? This tells us that the idea of an inscribed circle in a convex quadrilateral is intimately connected with the angle bisectors, just like it was for what? What do we know about the incenter of a triangle? The incenter of a triangle, the incenter of that inscribed circle and the triangle is what? Is where all the angle bisectors are concurrent. And we know that for a triangle, that has to exist, right? That's Seva's theorem, right? So we are able to get that. And the same thing is true in a certain configuration for certain configurations of convex quadrilaterals. Thank you very much.